Good morning. First of all, a comment. I just, this is really embarrassing, but I just found out just a short time ago that you guys haven't been able to access the class multimedia tab. Why didn't you tell me? Anyway, I got it. There's kind of an obscure switch way down buried in this in Genzabar that anyway I forget to go look at that, and somebody told me. I just went and turned it on, and it's there now. Also, I got lesson 2-1 up now. I still haven't had a chance to redo that. I still haven't had a chance to redo that part B of lesson 2-4. Half of it's there. You know, the second day of it, when I couldn't use my recording, I have to do that. Yeah, I just don't know when that's going to get done, but at least part of the lesson is up. Okay. Anyway, it's available now that I've turned it on. So, questions on 2-4. Let's see, this was the product rule and the quotient rule. I'll also tell you that the one today is going to be the beginning of a 2-day one. It's really important. It's the chain rule. Probably it's probably the most challenging rule, and so it's just going to take a little bit longer. If students have problems, they're more likely to have it with this one. So it's a big one, and we gotta try to get onto it. So 2-4 questions. Yes. 59. Okay. 59. You decide to form a partnership with another business. Your business determines that the demand for your product is inversely proportional to the square of the price. Okay. Okay, maybe interpreting what that means. Okay, inversely proportional means, well, here, let me just say this. This is directly proportional. Here I would say, if this is a constant over here, A is directly proportional to B, whereas here, C is inversely proportional to D. So I don't know how much you remember about that, but that's direct proportion, inverse proportion. Now, applying that here, it's inversely proportional. The demand X. I don't know why they call the demand X, but okay. The demand X is inversely proportional to the square of the price. Well, I'll tell you what. Why don't we just say D is demand and P is price. It's supposed to be colons. That thing always splotches on me. Okay, if that's the case, then the demand is inversely proportional to the square of the price, or cost, whatever they called it there. And then this is some constant. And we have to change the letters later. They call price, demand is X, so demand is greater than or equal to 5. They called it X. Okay, A, the price is $1,000. And the demand is 16. Well, that's going to let us find the constant. Let's see, what happens when you square 1,000? 1,000 times 1,000. I am blank. Just to make sure, it should be 10 to the 6, shouldn't it? and it is 1 million. Okay, so 16 times a million is, of course, 16 million. Now we know our constant. Okay. Find the demand function. Okay, so I'd go back here and go 16 million equals demand times price squared. And what did they want to call X again? The demand, X. So I don't know. Maybe I'll just leave it like that. So anyway, the demand is equal to 16 million divided by the price squared. So there's part A, the demand function. Now, they may not have used the same letters, but okay. Now, part B, your partner determines that the product costs $250 per unit and the fixed cost is $10,000. Okay, so that's telling you about the cost, isn't it? The hard part's going to be getting the letters right here. But anyway, the cost equation is pretty easy. That's, one more time, 250 per with fixed costs of 10,000. Okay, that's nice and easy. Now, the problem is going to be changing this into revenue. Do you remember? Revenue equals X times the demand, which normally is called small p. Okay, now my problem is how do we get X into that equation? They wanted X to be the price. Is that correct? One more time. What did they want X to be? The demand. Okay. I've already got the demand, but I don't have it in terms of X. I got to think about how to get these letters right. Hang on a sec. We got to get X in there. Maybe I just need to solve for X. Yes?
Okay, so the first one, make it P equals
Solve for P.
square root of each side. So P, 1,000 over the square root of 90.
And then they called this X.
Yeah, P. Oh.
Okay. Trying to think of the easiest way to do this without, I'll just go below here. Okay, so if we take this 16 million, 1, 2, 3, 1, 2, 3, equals X times P squared, and solve for P, now multiply by X to get the demand. So there's, what? The price, which is the same as the demand, isn't it? Yes. Okay, so there's P. Now, now we'll pull this guy in. Revenue equals X times the demand. And I get X times that. Revenue equals okay. And finally, ooh, that's going to really be ugly, isn't it? I guess we could, why don't we simplify that a little bit? We'll think of it like this. Revenue equals X times, okay, it's X to the first. What is this? X to the negative 1/2. And what's X to the first? Over, divided by X to the 1/2. It's X to the 1/2. So, in other words, this isn't as complicated as I thought. What's the square root of 16 million? So we have 4,000 X to the 1/2. Is that correct? Because if you took this square root, you'd have 4,000 over the square root of X. Yeah. Okay. Now this is a lot simpler. Profit equals revenue minus cost. So we have 4,000 X to the 1/2 minus this guy minus 250X minus 10,000. Okay, we finally got a profit equation. That's part C. And use a graphing utility to graph it. From the graph, what price? Okay, graph. So this time our function is, I gotta move this over just a tad, or up. There we go. So we want to do 4,000 times X to the 1/2 power minus 250X minus 10,000. Okay, I can see we got a parabola here. I'm trying to remember how to zoom. Yeah, here we go. Okay, so we got a graph that looks something like that. Now the question is, what price would you negotiate with your partner for this product? Okay. Well, what X would be the best? It's the vertex of that thing. I guess we're supposed to do that by eyeball. It looks like X is what? About 64, 65? And that's the number of units. So now you can go backwards and calculate the price. So let's just write that down. X is 65 approximately. Now what's the price? Back here, we'd have to come back in here and just substitute in 65. 16 million divided by 65. And then divide, and then take the square root of that. Looks like 496. So somewhere below, just a little below 500 bucks, according to this. So why did we do that? All right, let me just remind you, this was a profit graph. Why did I want to go to the top? Because it's a profit graph, I want the profit to be as high as possible. So I was looking for the vertex. At the vertex, using my graph, I was able to spot that the number of units, x, if you come down to the x-axis, and well, this nice thing about this program is it has a readout here. It says that x is 64.8. So I just rounded that to 65 because I was just eyeballing that anyway. And at 65 is the number of units you want to sell. Now go back and look at your price equation and plug in 65 units, and what does the price come to? And that's where I got the, I didn't write it down, but price should be 496, somewhere around 500 bucks. Okay, so a lot of stuff together there. And that should be it for that one. One more, maybe? One thing about the word problems, they have 3 parts to them. They take a while. Yep. Yes, 37. In fact, I think I've got it. Okay, here's 37. You were supposed to differentiate. Okay. Well, this is a quotient rule and a product rule, isn't it? Well, there's a couple options. What I did on the top is it looks like I multiplied, huh? I multiplied out the numerators. This is one approach. Do a little algebra first to see if I did that right. X cubed plus 2x squared plus x minus 3x squared minus 6x minus 3. Put that numerator together. X cubed minus 1x squared minus 5x minus 3 all over. Okay. Now I got it down to one thing over another. Now I can do the quotient rule. Derivative. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Let's see. Do I need to stop? Do you have enough time to do these derivatives? Can we do anything to simplify this? I guess I multiplied it out and tried to bring it all together. That's about it after that. I think probably the issue is not so much that as it is what happens up here, right? My guess? That's the big issue. Now, could I have done this another way? Oh my, there's a bunch of ways. I could have first done, I could have thought of this as one big happy product and said, take the first times the derivative of the second plus the second times the derivative of the first, and then when I did the derivative of the first, I would have had to done the quotient rule. So I could have taken that approach. And there's probably a bunch others. Yep.
We do 47.
Yeah, I don't know. Are we done with that one? Okay. 47. Yeah, here we go. 47. Find the points, if any, at which the graph has a horizontal tangent. So, how do we, well, before we can do anything with the tangent, we have to find the derivative, right? Which will tell us the slope. So, here we go. We got a classic quotient rule. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Okay. I'm not quite sure what this scribbling is over here, over on the left here. I'll get back to that. But anyway, does everybody see how I got this? Then it looks like I just hammered this out and started multiplying. So here we go. X cubed times 4x cubed is 4x to the 6th plus 4x cubed minus 3x to the 6th. All over okay, and the numerator then comes down to 1x to the 6th plus 4x cubed over that. Okay, there's my denominator in its pretty simple form right here. There's my derivative. All right, now, they wanted to know when the tangent line will be horizontal. When a tangent line is horizontal, what will its slope be? 0. Therefore, I knew that all I had to do is find out when this equals 0. All right. Now, you're probably wondering what happened to the denominator. I set this equal to 0. Well, I guess I showed it over here. Can't I just take this equation, set equal to 0, and multiply both sides by x cubed plus 1 quantity squared? And then it's goodbye denominator, right? So now I'm down to this. Well, now it's just algebra. How can I solve that? It's set equal to 0, so I'd love to factor it. I can. I can take an x cubed out, set each factor equal to 0, and then go from there. X is 0 over here. It's the cube root of a -4, which is actually a legitimate number. Because it's a cube root, you can take a cube root of a negative. So evidently there are two places when we get a horizontal tangent line. I don't know, were we supposed to do, yeah, that's it. So, I'm not sure what this is over here, so I'm gonna get rid of it. Didn't really make use of it today. Okay. Well, let's get a start on the new. So hopefully you got your quotient rule and your product rules down cold. The chain rule. The chain rule deals with composite functions. A lot of times functions are made up of composite parts. I'm going to just this is going to be a little bit of a weird slide, but it'll get you thinking about, I got on the left just straight old functions here. You don't need any chain rule to find the derivative of these. Here you would just use the power rule, quotient rule. Okay? The problem with the part on the right is we're doing two functions. We're taking a square root, and then under that we're doing yet another function. So it's almost like this is f of g of x, where f is the square root of x, and g is x squared plus 1. So I don't know if you remember composing functions, but you got to think in terms of composing and decomposing today. Okay? And to decompose this, you got to think of it as square root on the outside, and on the inside, x squared plus 1. Two functions. One like outer function, square root, and one inner function. Here again, the outer function is take whatever I give you and take it to the -1/2 power. The inner function says take whatever I give you and add 1. So again, there's an outer and an inner. Here we have an outer, take it to the 5th, inner, 3x plus 2. Outer, take something and square it. Inner, got a quotient, which we know how to deal with. Okay, so over here, these are all single, kind of like monotonic, one function. These are all two functions composed together. When you have composed functions and you want to find a derivative, you have to use what is called the chain rule. Now I'm going to skip ahead here. This, I think, is the best description of the chain rule. Here's pretty much how it works. If you want to take the derivative of a composite function, take the derivative of the outer function and multiply it by the derivative of the inner. So there it is in words. Okay? So if you want to take the derivative of a composite function, g of f of x, or what f of g of x, first take the derivative of the outer, that's the f prime, the outer function f, and then multiply it by the derivative of the inner. I'll let you get that down somehow. course, you're going to have trouble doing all this outer inner stuff unless you can spot the outer and spot the inner, and that's no small deal. You actually have to work on your vision. How is this one function and another? Sometimes it's not totally obvious. So you got to kind of sharpen your vision. Probably the best way to get into this is to start doing something. So I figure today probably that's mostly what we'll do from here on. We'll just dive in and do some composite functions and start differentiating. Everybody get that now? So one more time. To take the derivative of a composite function, take the derivative of the outer function and multiply it by the derivative of the inner. Okay? So here we go. I'm actually taking some from the assignment. Okay, so here's number 18. Y equals 3x squared plus 1. And that's raised to the 4th. Now, first of all, a point. Do we really have to think about inner and outer? Couldn't I just take that and multiply it by itself 4 times? Yeah. I don't know about you, but I don't want to do that. It's pretty, we could do it. You bet. Now here, but it's not just a point of what I don't want to do. It's making it more manageable. What's the inner and the outer thing here? What's the outer function? Take it to the 4th power, right? And the inner function is 3x squared plus 1. So if we follow what I taught you, to take the derivative, you would first take the derivative of the outer. So in other words, bring the power down. You guys know how to do the power rule. Reduce the power by 1. Okay, now complete the chain rule. We also have to multiply by the derivative of the inner function. What's the derivative of the inner function? 6x. Now our derivative is complete. Of course, you might want to hammer that out and get more detail, but without that 6x, we just don't have a derivative. There's your first example of a chain rule. I don't know, do you need to be convinced? Because then the next thing I could do, I wasn't planning on it, but if you want, I could. We could actually take that top thing, take it to the 4th power, take its derivative, and then show that the answer is the same as that y prime multiplied out. Do you feel the need for that? Yes. Yeah, most of the time we're going to want, I think we probably, in fact, we almost prefer it. Yeah, we'll get a feel for that. That's a real good question. You're going to have a little more trouble knowing when am I done. Yeah, we could go ahead and hammer that out and cube it and then multiply it by 4, but the derivative is really executed now. So for the most part, and my guess is, if the answer key has any sense, they're probably going to leave it like that. Maybe we should do an odd and just check, huh? I'll tell you what, let's do an odd nearby, and let's look in the back and get a feel for that. So, what's 17? Oh, I'm on the wrong lesson here. Okay. Let's do 17. And let's do it our way, and then let's compare. Okay, 17 is y equals 2x minus 7 cubed. Okay, derivative. Outer first, power rule. Multiply by the derivative of the inner. Now here they might do this. They might take at least the 3 and the 2 together And since this one is so easy, they might multiply that one out. I don't know. You know what I mean? It's just a...
Yeah.
Yeah, I forgot to do this. So, yeah, let's check in the back now. Let's see. Did they multiply it out? They didn't? Good. They have the same sense that I do then. Good. So you don't really have to, we're not into like polynomial drill here. Okay, let's go on. Next one. I want to do number 28. Okay, 28. We have y equals the cube root of 3x cubed plus 4x. Now here, I and the book would encourage a rewriting. I would think of this like this. Taking a whole thing, taking the cube root of a whole thing is the same as taking that whole thing to the 1/3 power. Now, here, there really is no alternative. I mean, do we know any way to take that cube root? You can't, like, take the cube root of the first term plus the cube root of the second term. There is no distributive property for exponents, okay? So, there really isn't anything to do here anyway. You'd be stuck algebraically. Now, when we differentiate, once again, do the outer first, which is the power rule. Bring the power down. Reduce the power by 1. That would leave us at this stage. And now, don't forget, multiply by the derivative of the inner function. Okay. Now, we probably want to... I and the book have a sense for not leaving negative exponents because I don't know, they're not totally clear. So I would simplify this a bit. What I would do is, let's see. Well, we got a 1 on the top and we have a 3 on the bottom from the 1/3. Doesn't this whole thing go on the bottom? And it's what? The cube root of a square. So we could write that like that. And then this 9x squared plus 4 goes on the top. And I could get that 1 out of there. But again, you really don't want to go any further than this. Yes?
So the bottom, could it be the same thing to leave it as 3 times the quantity 3x cubed plus 4x to the 2/3 power? Would it be the same?
Yeah, usually we don't like to leave fractional exponents either. But yes, that would be the same. It would be true. You said 3 times, and then you started over.
It will be 1/3 and then on the bottom.
Oh, that 3. Gotcha. Yeah, we could have said quantity 3x cubed plus 4x to the 2/3 power. That would have been okay, but the book doesn't kind of regard that as being done then. So, in effect, the bottom line is the book doesn't like negative exponents and they don't like fractional ones. So, when you get all done, you got to kind of translate out of that, like we did. And I think, I'm not trying to belittle the book. I think they probably have arrived at a good point for simplifying. Okay, let's do 34 next. F of x is equal to 4 minus 3x to the negative 5/2 power. So that's, I believe, the way it's stated in the book. So when we find the derivative of this, okay, we're going to do the outer function first, and the outer function is what? Something to the negative 5/2 power. So we're going to use the power rule. Reduce the power by 1. What will that cause the power to be? Right. You have to go down 1, which is like going down what? 2/2? Yep. All right, now let's just try to get this in a non-fraction power and non-negative power form. So once again, let's get the negative 5/2 in position. Oh, you know, I didn't do the chain rule, did I? What's the rest of this? Got to take it times the derivative of the inside, so there's got to be a -3 there. Okay, so there's another -3 on the top, right? On the bottom, we're going to have what? How should we write this? Well, it's what? The square root of 4 minus 3x to the 7th? And so we're really done. I mean, the only thing I would do is change the numerator then to what? Positive 15. Can't cancel anything. So, questions? Number 40. Okay, 40. F of x is equal to 4 minus 3x squared raised to the negative 2/3 power. Oh, by the way, there's more to 40. 40 doesn't just say find the derivative. It says find an equation of the tangent line to the graph of f at the point 2, f of 2. Well, so we got to do a lot more on this problem than we've had to do before. Got that? So we got to find the derivative, but what are we aiming at? The equation of the tangent line at the point 2, comma, f of 2. Okay. So step 1, find derivative. And we have ourselves a composite function here. Find the derivative of the outer function. One less than negative 2/3 would be negative 5/3. And then the chain rule. We're going to multiply by the derivative of the inside function. Okay, let's get that thing simplified a little bit. Got negative 2 on the top. We have 3 on the bottom. We've got a negative 6x on the top. We've got what? The cube root of 4 minus 3x squared to the 5th. And then the top just becomes what? 12x? Actually, we can simplify, can't we? 12, we can cancel with the 3 and just get a 4. So I will rewrite this one more time. And that's supposed to be a 5th power under there. Try that again. and then this root sign goes over it. Okay. I think that's as simple as we're going to get. Okay, now that's as good as we can do at the moment for our derivative. So that's f prime of x. Now, they asked us to find the equation of the tangent line to the curve when x is 2. So, wouldn't we want to know f prime at 2? Okay, so take your formula from right over here, and what's f prime at 2? Oh, wouldn't you have an 8 on the top? What would you have on the bottom? Well, let's hammer it out. What's 2 squared? 4. 4 times 3 is 12. What's 4 minus 12? Negative 8. What's the cube root of negative 8? Negative 2. And what's negative 2 to the 5th power? Negative 32. I'll explain that. Okay. You're probably wondering, why did I take the cube root before I took the 5th power? Okay. When you have something to the 3/5 power, 5/3 power, you can either, it doesn't matter which order you go, you can take it to the 5th power and then take the cube root, or you can take the cube root and then take it to the 5th. So when I got down to negative 8 right here, I took the cube root first. What's the cube root of negative 8? Negative 2. And then I took the answer negative 2 to the 5th. You can do it the other way, just that you got to deal with a lot bigger numbers then. Yep.
Is that rule true for everything?
Yeah. Well, anything to a fractional power, in effect, you can do the top, the numerator first, or the denominator first. That's a general go, yeah. So, what's a simplified version of this? Okay, so what have we found out? We found the slope of the tangent line at the point they wanted us to. Okay, we're almost there. We're supposed to find the whole equation. So now we know this. What? Y equals, in slope-intercept form, we know the slope. We just don't know b. And now we got a little problem. We need to find out what is f. You know, they told us at 2 f of 2, but we really need to know what f of 2 is. So we got to go back to the original. What is f of 2? Well, what's 2 squared? 4. 4 times 3 is 12. 4 minus 12 is negative 8. Okay. What is the cube root of negative 8? Negative 2. And what's negative 2 squared? Positive 4. And then because it's to the negative power, it's 1 over that. Did you follow? Okay, that's a reason why negative exponents aren't the best. When you get all done, what does the negative part of the negative exponent mean? When you get all done, divide it into 1. So I got a 4, so I had to write. So now, plug the point in and solve for b. Negative 2/4, which is negative 1/2. So isn't b 3/4? So therefore, that should be our, okay, I think we're going to take a look at this one on a graph too. I think you were supposed to show on a graph, see if that really makes sense. Okay, so that line we just found should be just barely kissing our original function at one point, and according to our calculations, should have a slightly negative slope. Here we go. Yeah, I gotta zoom way back in. I don't even know where we are. Well, eventually I'm going to get there. Let's see, I got to zoom in, right? It's not doing much zooming. Okay. I can't remember how to reset the axes. What's that? I don't know, that's not doing much either. Well, I gotta just, boy, that's gonna take forever. Now let's zoom. I'm sure there's a quick way to do this. I haven't. Let's, here, how about this? No, that didn't do it. I've already got the graph drawn, so it shouldn't take that long once I get down. I don't want to kill you. Sorry. We still got a minute, so I'll get there. 700s. $400s. Okay, there it is. The like upside down M, that's the original function. And the red curve is the tangent line that we calculated. And you notice how at x equals 2, comma 1/4, it's just barely kissing it, just like we said it would. Okay. Thanks for hanging on for the exciting conclusion. You know, I would just suggest it wouldn't hurt to start on the assignment, even though I'm not giving you one yet officially.